I am Dr. Mahendra Motilal Dongudi, Professor and Head of Department of Mechanical Engineering, Barry's Institute of Technology, Mangalore. Today I am going to discuss about the surface tension. Surface tension, it is the property of fluid. Right? Surface tension is a property of static fluid. To understand surface tension, I have taken a static fluid here. I have taken a container. 1, 2, 3, 4 is a container. This is filled with the liquid, and it is having a top surface. Liquid is having a top surface that is called as a free surface. This free surface is having a tensile force across the free surface, edges of free surface, right? Having a tensile force. Right? When force acts across the tensile force acts across the edges, right? The free surface acts like a solid surface. Once again, I repeat this: the free surface of liquid, right? When the tensile force acts across the edges of free surface, when tensile force acts across the edges of free surface, the free surface acts like a solid surface. This process is called as a surface tension, right? Edges of free surface is having a tensile force since the surface is acting as a solid surface. One example also I'll quote. You take a A4 size or some sheet of paper, stretch it, apply the tensile force across the edges. Once if you apply the tensile force across the edges, paper becomes very stiff, means it becomes like a solid surface. We can keep a lightweight materials on the solid surface, sheet of paper. Even if you throw a plastic ball, small ball, it will bounce back because your paper no acting as a solid surface. Same thing happens in the liquid. Free surface acts like a solid surface. When the tensile force acts across the edges, just remember this. Why this tensile force acts across the edges? Which is that force acting across the edges? It is important to understand. If you understand, then we can speak about the surface tension. Here there is a unbalanced, a cohesive force where near to the free surface. Take a free surface, right? It is not a flat, it is bulged. It may be concave or it may be convex. It is not a flat. Because the tendency of cohesive force, it is because of tendency of cohesive force. In particular case, if you take a water as an example, tendency of what? Tendency of cohesive force is in downward direction. So surface, free surface is in the convex shape, right? One force is pulling your free surface in downward direction. Other force, that is adhesive force, is acting in opposite direction. Adhesive force, that is force of attraction between surface molecules and the water molecules. It is in opposite direction, right? It is making to stick your free layer to the the container surface, right? Other side, cohesive force is pulling downwards. This creates a tensile force in the free surface, right? Across the edges, we find a tensile force, right? So your free surface acts as the solid surface. This is all. This is what all about the surface tension. Now we are discussing about the relation between P and sigma, right? Sigma is the surface tension, P is the pressure. Due to this pressure, there is a pressure force, right? Now we have to understand what is the pressure, what is the sigma, right? And how to equate, why to equate, all that we have to understand, right? We are finding P and sigma relation for water bubble, soap bubble, and water jet, right? Here I have taken a container, right? In the container there is a liquid I have taken. It is an example for the static fluid, right? Above the free surface we find a air media, right? There is a water, this is the free surface, it is all air around it, right? So atmospheric pressure is acting on the free surface. Atmospheric pressure is acting on the free surface. This atmospheric pressure always acts normal to the surface. That is the pressure force is acting normal to the surface. And you know about the surface tension that we discussed it in the previous slide, right? This is the surface tension. Here in this particular case, water bubble, right? It is opposite direction. It is in the opposite direction to the P, right? P is normal to the surface and it is opposite. Directly we can equate both in this case. The magnitude wise both are equal, direction wise both are in opposite direction. So if we equate both, right, we're going to get a what the relation between P and sigma, right? First I take a water droplet, it is a water droplet, and I split that water droplet into two equal parts. On one equal part I'm showing here the surface tension, right? And pressure force. Pressure force is acting on the surface, right? It is a P is a pressure. Due to this pressure, there is a pressure force. If you multiply pressure with the cross-sectional area, we get a pressure force, right? So it is sigma. It is what Newton per meter. If you want total sigma, then I have to multiply this by the circumference. That is what I have done. It is Newton per meter into meter, so I get Newton, right? So if you want total surface tension, then sigma I have to multiply with the circumference. That I have done, right? So it is the pressure force now. It is a force due to surface tension. Both are equal in magnitude, opposite in direction. Though, so I am equating. Thereby, I get the relation between P and the sigma for water droplet, right? Now I take a soap bubble. Soap bubble means here inside also there is a air, outside also there is air. So surface tension has to be multiplied by two things. Inside also there is air media, outside also there is air media. So this pressure force is equal to twice the surface tension, right? So just you equate both, we get a one more relation for P and sigma. It is for soap bubble, right? Similarly, water jet, it is a water jet. For this water jet, right? It is a water jet. Right? It is a water jet. What I want to see here, it is a water jet I have shown. I split this water jet into two equal parts. So on one equal part, I show you the surface tension, right? I am showing you surface tension, right? And I calculate the pressure force first. How to calculate pressure force? Pressure force is equal to P into this cross-sectional area, right? This cross-sectional area. That cross-sectional area is nothing but the L into D. L into D. I got the what? I got the surface area. P into surface area is nothing but the pressure force. Similarly, I calculate the surface tension, total surface tension, right? So total surface tension is equal to sigma into 2 times the L, right? You may ask why 2 times the L, why not you consider this D, example, if you take a pipe jet, water jet example I'm giving you. If you take a pipe, if you press the outlet of the pipe in uh, vertical direction, if you press in vertical direction, water will expand in the horizontal direction, only horizontal direction, right? If you press in the vertical direction, the surface tension is in the horizontal direction. That is why surface tension I have considered along the L only, right? Along the L I have considered the surface tension. That is why total surface tension is equal to 2 into sigma into 2 times L I have taken, right? Then I equate the pressure force and the surface tension, total surface tension. Then I get the relation for P. P is equal to 2 sigma by 4. It is for the water jet. P is equal to 8 sigma by D for the soap bubble. P is equal to 4 sigma by D for the water droplet. Right? It is a relation between P and what? P and sigma.